morning, learners back there at home. I hope you are enjoying your holidays. I hope and believe that you're keeping safe, observing the protocols that have been advised by the Ministry of Health. I am Mr. Waititu Robert. I'm a teacher of physics. I teach physics and mathematics, but for today's lesson, I'll be teaching physics. I teach in a school called Kahogoine Boys. The school is in Kiambu County, in Gatundu South Sub-County. Today's lesson will come from a topic, a very interesting topic in Form 2, which is called Hooke's Law. Under this topic, I will be putting more emphasis on finding the constant of springs. I have some resources with me on the whiteboard. We'll review Hooke's Law, but point of focus where I will concentrate much is on the spring constant. More so on finding the spring constant of springs that are arranged in series and springs that are arranged in parallel. Now, to bring us to book, Hooke's Law is a discovery or a finding which we might take as a common finding that relates the extension of a material that is elastic. How much will it stretch given the force that will be provided or the force that will be stretching it. It's a comparison. We try to find out how much will the spring stretch or a material that is elastic stretch whenever we subject it to a given force. The findings were found by one scientist called Robert Hooke, in which he said, or he found out that force will always be proportional to extension. Force will always be proportional to extension. And when we got deeper into this concept, the symbol of proportionality, learners, is not a conventional symbol in mathematics, as we know. And therefore, we need to substitute that symbol of proportionality with the conventional symbols. And the conventional symbol we are going to come up with is the equal sign. In substituting then, F will be equal, we introduce a constant K, which will be multiplied by extension. We have substituted the symbol of proportionality with the equal sign and then brought in the constant K. Our point of interest will be this K. The finding of Robert Hooke in his statement, which we call the Hooke's Law, he said, for any material that is elastic, and in this for helical spring or any other elastic material, the extension is directly proportional to the applied force, provided that the elastic limit will not be exceeded. Whenever you have a spring and you stretch it to a certain extent, if you withdraw the stretching force, that spring is going to regain its original shape and size. But normally, and this will even come from some life experiences, if you extend it beyond what it can be able to manage, the force that it can be able to manage, upon withdrawing the force, that spring will not come back to its original size and its original shape. Now, within that section where it can be regain the shape and size, then force will always be proportional to the spring's extension. For instance, in very simple terms, if I expect a force of 2 newtons to give me an extension of 5 centimeters, if I happen to triple my force and I take my force to 6 newtons, then I will expect also the extension to triple, which will become 15 centimeters. That the force applied will always be proportional. I double the force, I double the extension. When I triple the force, I'll also triple the extension. And now, to get us now to our concept of arranging springs, either in series arrangement or the parallel, we need to know how to find a spring constant. And this spring constant is what I've said is our K, and therefore, we will always be able, or will be required at all times, learners, to make our constant K the subject of the formula. And in this, K will be equal to F over E. I've divided by extension to the right side of the equal sign, also divided with E, or extension, to the left side of the equal sign, and made K my subject of the formula. Getting these to real examples, I want you to work with me and follow closely, learners. Taking an example that I will give, we work together. The first example that will help us be able to know how to find the spring constant K, take this down. What is the spring constant? What is the spring constant of a spring that extends 25 centimeters? What is the spring constant of a spring that extends 25 centimeters when a force of 2 newtons is applied on it? I will extract what is given. We are told extension here from the statement is 25 centimeters. Again, from the same statement, the force that is causing that extension is equal to 2 newtons. We are required to determine the spring constant. We'll come back to our formula that K is F over E, and in this K is equal to force over extension. But I've captured something there that is very important. Our extension is in centimeters. Our extension is in centimeters. We need to always have length being converted to the SI units, the conventional units for measuring length. Any length, extension included, is measured in meters, and therefore will be required to convert these in meters, and simply our 25 centimeters will become 0.25 meters. In this, I've divided centimeters, rather 25, with 100. After that, I will substitute this to my formula that the force is in newtons. Extension, we have found it to be 0.25 meters. In dividing those two, I'll have 200 newtons divided by 25 meters. Remember, I've multiplied by 100 to the denominator and 100 to my numerator. In reducing this, if I divide by 5, I'll have 5 there. In the numerator, I'll have 40. If I divide by 5, 45 will go to 48 times. And the answer I'll get there will be 8 newtons per meter. Or rather, 8 newtons per meter. Very important, again, concept that has been brought to us, that the units for the spring constant are newtons per meter. What does this communicate to us? The units, whenever we are provided with units, what do these communicate to us? 8 newtons per meter tells us that we will be required to provide a force of 8 newtons for this particular spring to extend by only 1 meter. Therefore, this information gives us or tells us or communicates to us how strong a spring is, or any elastic material is, or how weak that spring will be. When we have a number that is larger, if I was to give a comparison, given a spring of 200 newtons per meter and compare it to this one that we have calculated, then for this second spring, we are going to need a force of 200 newtons to have it extend by only 1 meter. In this other one, we only needed 8 newtons as a force to extend it by 1 meter. And therefore, the second spring, according to the units, is a much stronger spring. Very important, the units for the spring constant. Now, moving ahead, I would wish us to take this second example. We take our second example. Learners, hope you're moving along with me. And the second example that you're going to have, a spring whose constant K is 180 Newton per meter. A spring whose constant K is 180 Newtons per meter. Newtons per meter extends by 1.5 meters. Extends by 1.5 meters. When a force extends by 1.5 meters, when a force F is suspended on it. When a force F is suspended on it, find that force F. So we do not have F. Remember in the first example that we have had, we found the spring constant K. But this time, we have been provided with the spring constant K. And also, we have been provided with extension. And what we are required is to find a force that will be able to cause our spring to extend by 1.5 meters. Again, we go to a formula that F is the product of the spring constant multiplied by extension. These have been provided, and therefore K, 180 newtons per meter. That will be multiplied by 1.5 meters. If you look at the units that I've had, I will be able to cancel the units for extension or length, since meters in the first part is in the denominator and in the second part is in the numerator. I can cancel those two. Now, the best thing about these learners is when you have the correct formula and then you substitute it, if you find that you'll be confused by the units, you are allowed to have the substitution done without including the units. But the final answer must have the correct units. So having cancelled out the units for extension or length, then I'll have 180 multiplied by 1.5, and this will give me 270 newtons. Remember, the question was, we find force that will cause an extension of 1.5 meters to a spring whose spring constant is 180 newtons per meter. From the same question, we have another part in which you can add these from the question. Again, find the extension when a mass of 9 kilograms is suspended on the same spring. Find the extension when a mass of 9 kilograms is suspended on the same spring. In this, some information is also captured that the gravitational force or gravitational pull is equal to 10 newtons per kilogram. So, from the information, the same spring, meaning the spring constant will not change, will remain the same. We do not know of the extension, but we are given the mass as 9. From the question, we have 9 kilograms. So we are looking for the extension. That one we do not know. Again, we come back to a general formula. What we are required to find is extension, and therefore, we are going to make extension the subject of this formula in a similar way we did in making constant K the subject of the formula. And therefore, we're going to divide by K on both sides, and we're going to have extension will be equal to force over spring constant K. So from this formula, E is equal to F over K. I will add a but there. Why have I added the but? We are given mass, but not force or weight. And therefore, but mass is given as 9 kilograms. We cannot substitute for F with 9 kilograms because the formula dictates we have a force, but not a mass. And therefore, we'll be required to convert our mass into force or weight, in which we say weight is equal to force, which is also the product of mass times gravitational force. They have given us a gravitational force G as a constant, and in substituting we'll have 9 kilograms multiplied by 10 newtons per kilogram. Again, the units for mass will cancel out, and we're going to have 9 multiplied by 10, which will give us 90 newtons. All these steps will be awarded as you work out. And therefore, having converted our mass to force, we can substitute in our formula, where extension is force over spring constant K. In this case, our force has been found to be 90, and our spring constant was given as 180 newtons per meter. Our units for force will cancel out. We have newtons to the numerator and as well as newtons to the denominator. What we are remaining with are meters. But if you look closely, having cancelled the newtons, we are remaining with 1 over meter. If you were to take 1 over meter to the numerator, then we are going to have a reciprocal of the same, and we are going to have meter over 1. And therefore, our units for extension will be in meters. In reducing these, we are going to have 9 going to 18 2 times, and a half converted to a decimal notation will be 0.5 meters. Simple concepts, and we usually say these are areas where students can maximize in scoring marks, since the concepts are not all that complex. You're required to remember the formula. When you have the general formula, you can always play with it and then be able to establish or find out the unknown, either the constant, the force, or the extension, as we've done in our example at that point. Now, this information is an introduction to the concept that I would want us to dwell or take some time on, where we are dealing with a spring. This is a single spring that has some force applied on it, and it is extending or having an extension of a certain sort. But when we have more than one spring, when we arrange these springs, we can arrange them in the two arrangements that I've presented or drawn. We can have them in a series arrangement from my first diagram. In these, I've only drawn 2 springs, implied by S1 and S2. S1 stands for spring number 1, S2 stands or represents spring number 2. In these, we'll be expected to find the total extension that will be achieved from the 2 springs. Remember, we are not only confined to arranging them in a pair, only having 2. We can even have very many of these springs arranged in series. But the concept we are going to learn here can be applied in all of those arrangements. Now, in a situation where you are presented with only a single spring, you're only presented with a single spring, there's a lot that we can learn from this, from the introduction we had, especially on Hooke's law. Whenever a spring is subjected to a force, we are going to achieve a given extension. So in a single spring that has been suspended, getting the extension will be very easy, since we'll only be required to know the spring constant K. I'll give just an example. If this spring that we're presented with has a constant of 10 newtons per meter, and we suspend on it a force, I'll just give a random number, a force of 8 newtons. spring constant 10 newtons per meter. We are suspending a force of 8 newtons. What do we expect to be the extension achieved for a single spring? Given the constant, extension we have found from our formula is force over K. All the values are in the SI units, force in newtons, K in newtons per meter. And therefore, I can substitute 8 newtons divided by 10 newtons per meter. And in this, I'll have 0.8 meters. It will be as simple as such. In other situations, you will not be given a spring constant. It will be unknown. But you'll be provided with force and a given extension. In finding again K, you'll be required to divide force over extension. Remember, this is happening in a single spring. Now, when we have them 2 or more and in series, normally what happens is the first spring S1 will be carrying a load of 20 newtons. And in this case, as if spring number 2 is not there, we'll be having spring S1 carrying the load of 20 newtons, as if our S2 is not present. And therefore, its extension, it will behave as if it is carrying the load of 20 newtons alone. So S1 will have its own extension. If these springs are identical, identical means they are of the same spring constant. Apart from that information, they were initially of the same length, have the same spring constant, meaning they are of the same strength, and they were initially of the same length. None of the two springs was longer than the other one, meaning they were identical. If you're provided with a spring constant, how are you able to achieve or find the extension? I've said in this, we only treat individual spring as if it is carrying the load individually, alone, without being assisted by the other. Our S2 as well will extend as if it is carrying our load of 20 newtons, as if S1 is not there, implying it has been connected to the support. And therefore, in this case, whenever we work series, we treat springs individually. That is the concept I want to drive across. And we work extensions per spring, and then we multiply or we add the individual extensions. We'll use the diagram I have on board as our example, in which we are given the spring constant, and we are given the force causing the extension in the two springs, and therefore, what will be our total extension, E1. Very important to you learners. It is good when you are working these to carry the examiner with you, the person who will be marking for you. Carry him along. Let that person see what my learner was doing, what was he or she working on. So we will talk of the upper spring or extension of the upper spring. So in this case, extension will be equal to force over spring constant. The reason why we had to review the use of our formulas. And from the information given, we find we have a force of 20 newtons, and the spring constant again is given. So we have 20 newtons, for which the spring constant is 100 newtons per meter. Cancelling out the units for force, then we're going to have 2 over 10, which will give us 0.2 meters. Remember, our upper spring has extended as if the lower spring is not present. Again, the lower spring will have to extend as if the upper spring is not present. And therefore, we'll also carry the examiner with us and talk of the extension of the lower spring. So again, extension will be equal to force over spring constant K. The force applied is 20 newtons. The spring constant is the same, 100. And in cancelling out, we'll still have another 0.2 meters extension. Now, the extension of both springs will be the sum of individual extensions. And therefore, again, directing the person who is marking your work, that total extension, in this case, will be 0.2 meters added to 0.2 meters to give us 0.4 meters. I would wish learner to maintain or retain the working for the series connection, to have a comparison. We get a comparison. How do we treat arrangement of springs whenever they are arranged in parallel? So I will try to maintain the working there. In giving the working of the example, I've tried to maintain the force such that we can have a comparison. We can have a good comparison. The springs are identical. If you look at the spring constant in both cases, where we arrange them in parallel, we still maintain 100 newtons per meter as the constant of each of these springs. The force applied again is 20. Therefore, what do we expect to be our extension 2? Now, whenever springs are arranged in parallel, each of these springs assists the other in carrying the load. In this case, one spring could have extended more, but when we look at this diagram, the two springs are assisting each other in carrying our load. And therefore, we do not expect these two springs to extend as much as would happen with one spring, since both are assisting each other. And therefore, our answer for extension 2, we expect it to be less compared to extension 1. But you cannot have the concept or understand the concept. You have to present the same understanding in terms of the workings that you will do. Now, how do we approach this? Now, the spring constant K of springs arranged in parallel, spring constant K of springs, whenever we arrange them in parallel, my subscript P stands for the parallel arrangement of springs, is given by the formula N multiplied by K. Remember, our K is the constant introduced previously of a spring. In this case, we are given the spring constant K as 100 newtons per meter. And therefore, since our springs are only 2, N stands for the number of springs that will be arranged. The number of springs that will be arranged in that parallel. We can have them 2, we can have them 3, or we can have them more. And therefore, our N is not a constant, will keep on changing. You only count them, and then you place it at that point, and then you have your spring constant. And therefore, our combined spring constant for the parallel arrangement in this case will be 2, since we can count the first one and the second one, multiplied by the provided spring constant of 100 newtons per meter. In multiplying, we are going to have the spring constant being 200 newtons per meter. Remember, even working overhead without even taking a pen, you can tell if this one spring extended by 0.2 meters, then when the two of them are assisting each other in lifting or carrying the same load, we expect the extension to be half, because they are assisting each other. They have the same strength. One of it extended by 0.2. So when they are assisting each other and there are two of them, then the extension will be half the extension for one spring. And therefore, we expect the answer to be 0.1. But we cannot present such to an examiner. We have to show the working. What is it that we did such that we came up with the answer? And therefore, our extension, in this case E2, will be force divided by the spring constant that we have found for the parallel arrangement. And the force is maintained as 20 newtons from the chart, and then the new or the found spring constant 200 newtons per meter. In cancelling this out, we have the units for force, and then the 0 will cancel out. 2 will go to 20 10 times. 1 over 10 will give us 0.1 meters. The answer we have found agrees with our expectation, what it is that we thought. One spring extending by 0.2 meters. When we have two of them assisting each other, then the extension should reduce. or should go to half. Half of 0.2 is 0.1. Now, our workings or finding solutions for such arrangements do not end at that point, since we can have a combination, springs arranged in parallel together with others that are in series to each other. And I will wish you, learner, to follow or work with me very closely in our third example, where we are going to have more springs. We have added more springs. Remember, this is a combination of both springs that are arranged in parallel to each other. They are assisting each other. And in the same setting, we have them in series. Note, we have an upper block or arrangement of springs. We have another arrangement in the middle section, and we have on the lower section still some arrangement of the springs. So we have a combination of both parallel and series connection. In now finding our total extension, what do we expect to be our total extension? We are going to treat each arrangement in the lower middle section and the upper section separately. We work each separately, and finally we are going to add our extensions to get the total extension E3. Carry the person marking for you along with you. Tell them what it is that you're doing in that particular time and moment. So we'll start with finding extension So we are going to have, or to work first, the extension of the upper block, for which we find the number of springs. We have spring number 1, spring number 2, and spring number 3. And therefore we have 3 springs that are arranged in parallel to each other. More to it, we are told all these springs are identical, and the spring constant is also provided. We are told the spring constant of these, all the springs, is 150 newtons per meter. And therefore, we are going to come up with our formula where the spring constant of springs arranged in parallel is the number of springs multiplied by the spring constant of each of those springs. So in this case, we have 3 in the upper block multiplied by the spring constant provided, which is 150 newtons per meter. Remember, multiplying 150 with 3, we get 450 newtons per meter. So the spring constant of these 3 springs, they are going to behave as if it is a single spring that is much stronger compared to one of them. A single spring that is much stronger, and its spring constant is 450 newtons per meter. So in finding the extension of the upper block, we are going to have force divided by spring constant K. Remember, this is K of springs that are in parallel. The force, 90 newtons. In the series connection, we said the upper block will behave as if there are no other springs that are supporting the load below it. It's as if you have taken our load and suspended it beneath or below the 3 springs that are connected in parallel in the upper block. And therefore the force will be 90 newtons divided by the spring constant that we have worked out as 450 newtons per meter. In cancelling this out, you're going to have 9 goes to 45 5 times. 1/5 converted to the decimal notation will be 0.2. Remember, we are working extension that is given in meters. That is the extension of the upper block. Now, what is the expectation when we come to working the other extension? One fact from the concepts that you already have or learned this morning is that the middle section or the middle block will have to extend more, since we have fewer springs that are carrying this load. We do not expect to work the extension of the middle block and find that they're extending less compared to the upper block. In this, they were assisting each other, the three of them. We are only having two. Therefore, we expect them to extend much further or more compared to the upper block. In the lower section, the last spring that will be carrying this load is carrying the load alone. And we expect it, or rather this spring, to have the greatest extension of the three in comparison to all the other sections. Now, in working so again, we said we will always move and direct the person who is marking for us such that they can see in all these areas. Remember, you get awarded marks in working out all areas. In each of these parts that you are working, in finding the extension for the upper block, you have marks that you'll get. In working the middle section, again, there are marks that will be awarded. And eventually, when you get the total extension, you are going to get your final marks. So it is good to have the examiner follow what it is that the learner is doing. Now, we are going first to work the spring constant of the middle block, in which we say the formula is n, the number of spring, multiplied by the spring constant of each of those springs. So in substituting, we have n. We can count the springs are only 2, multiplied by the spring constant of 150 newtons per meter. When we multiply 150 with 2, we get 300 newtons per meter. Again, the extension will be force divided by spring constant of the parallel arrangement. The force, again, 90 newtons, will be carried by the two springs as if the other springs are absent. To be carried by the two springs as if the others are not there. Therefore, the force will be 90 newtons divided by the spring constant that we have worked out, which is 300 newtons per meter. Then we have 3 going to 30 10 times and going to 9 3 times. 3 over 10 will comfortably give us 0.3 meters. By inspection, you can comfortably say what your workings are correct, since the expectation was that the two springs will extend or stretch more compared to the 3 springs. And we have found 0.3, which is larger than 0.2. In the same manner, we expect one spring to extend the greatest. So the answer that we are working last should be larger than 0.2, should also be larger than 0.3. Now, the final spring, its working is very easy. It's only one spring, and therefore, we only guide the examiner that we are working the extension for the lower spring. And in this case, it is carrying the load individually. And therefore, extension will be force over spring constant. The force being carried is of 90 newtons. The spring constant is 150 newtons per meter. Then 3 will go to 15 5 times. It will also go to 9 3 times. 3 over 5, converting these will give you 0.6 meters. I believe from inspection this answer is correct, because if one spring is extending by 0.6, when two of them as helping or supporting or assisting each other in lifting of the load should extend by half, and 0.3 is half of 0.6. And therefore, through inspection, our answers are correct. Remember, the interest was us working out the total extension, E3. So, again, take the examiner with you that you are now working the total extension, which in this case is our E3, which is the sum of the individual extensions of 0.2 meters plus 0.3 meters plus 0.6 meters. Doing the summation of 0.9, this will give us 1.1 meters. So that is the expected total extension, for which the upper block extended by 0.2, then the middle block extended by 0.3, and finally the lower block extended by 0.6. In adding all those extensions, we have 1.1 meters. We need to do very many examples when we have the combined arrangement, since in most of these exams, most of the exams that you're going to come across, they will not give you just one spring or two in series. They will have a combination of all the springs, or rather they'll have a combination of parallel and series. In this case, I've not limited the combinations to what I've drawn. We can have one in the upper block, we can have three in the middle block, in the lower block we can have one or more. We can even not have all these. We can have two sets of springs where we have a number in the upper block and another one in the lower block. So a student should not only confine him or herself to what are the examples that I've presented on the board, but getting to understand what are the workings that rather the procedures that we follow in working out, such that you can be able to tackle any of these examples. Now, we'll be doing further examples. I'll provide further examples of which I'll expect learners to continue working with me. And again, ask you learners back there at home, as you continue enjoying your holiday, you can send through the questions. If you look at the screen of your TV, you'll find the number. If you send a question to me, it will be able to reach me and I'll be able to answer you in the time that is remaining. Please send in your questions. The number will be presented and I'll be able to answer you within the time that we have. So take down these further examples. Learners, take down the further examples that we have. Find the extension caused by a mass of 4 kilograms. Find the extension of a mass caused by a mass of 4 kilograms in the diagram below. So very fast, we have some two springs that are carrying a mass of 4 kilograms. So the learner is required to find the total extension K, given that the spring constant of each of the springs is 10 newtons per meter. From this, if you compare with what we have done in this other section, you'll find the work is much. You have an easier question to tackle in this case. But what are the requirements? What are the procedures? What is it that will be marked by the teacher? In this case, we need one to find the combined spring constants of the two springs. Remember, the two are arranged in parallel. They are arranged in such a way they are lying adjacent to each other. So, being in parallel, we find the combined spring constant. In this case, we have 2 multiplied by the given spring constant of 10 newtons per meter. And in this case, we are going to have 20 newtons per meter. In finding the extension E, we need to divide force with our newly found spring constant. But note that the force is given in form of mass, and therefore we need to convert our force into, or rather our mass into force or weight. Therefore, we'll talk of, but force will be equal to weight, in this case a product of mass times gravitational force. Our mass is 4 kg Previously, we had been given the constant G, or gravity, as 10 newtons per kilogram. In cancelling that, we have 40 newtons. And therefore, you will be awarded for converting our mass into force and having our force in the correct units. Then, applying our formula that extension is force over spring constant, force 40 newtons, spring constant, K that we have worked out will be 20 newtons per meter. Cancelling out the units for force, we remain with 40 over 20. The zeros will cancel out, and therefore 4 over 2 will give us 2 meters. So what will the examiner be interested in working out or in marking your work for this question? One is that you remembered to convert your mass into force, because from the units of the spring constant, we said there is communication that we get newtons per meter, or rather all this information, newtons per meter, gives us the strength or tells us how strong that spring is or how weak that spring is. And therefore, we must always have our units in newtons for force, and we must always have our extension in meters, and therefore given other units for length, meters, millimeters, or even larger values for extension, you have to convert them to meters. Now, we can look at our final example, learners, in the time that we have. We look at the very final example from the same arrangement. And this one is very important. Find the work done by the force in stretching the springs. Find the work done by the force in stretching the springs. Another concept that summarizes the topic. Another concept that has come up is finding work. Remember, many times we equate work to energy, and therefore, if this question was to be substituted and you are asked the energy of the springs, it will mean the same as work. And the reason why we equate work to energy is because both have the units which are joules. Joules abbreviated, or the SI units, or the symbol for the SI unit is capital J. And therefore, we need to be directed or guided by the formula for finding work. And the formula for finding work is a half force times extension. Another formula that has been introduced to us, work is a half force times extension. Other times, there are some time you'll find you are not provided with force and extension. So from the same formula, we can substitute. We found F is also a product of K and E. And therefore, I can substitute F with KE in our formula for finding work or energy. Hoping you're following. So in substituting F, I'll have work will be equal to a half. Bring in the value for F, which is the product of KE, and then we multiply by extension. And generally, the formula will become a half KE. E times E is E squared. Two very important formulas, learners. If I were you, I would take these formulas down and retain them, because for you, your work will not be much. You'll only be required to remember how to state the formula, get the values provided in the questions, and then substitute from the formulas. So from this, in finding work, we can use the first formula, a half FE. Why? We already know the force, which we found as 40 newtons. We have also found the total extension that we have worked as 2 meters. Or I can opt to go for the second formula, since I had worked the constant K and the extension that I've worked and found to be 2 meters. So in using the first formula, work will be equal to a half times force, 4 kg converted to weight became 40 newtons, multiplied by the extension that you have worked of 2 meters. And in this, dividing by half, we're going to have 40 times 1, which will give us 40 Newton meters or 40 joules, capital J. Remember, units for work or energy can be Newton meters. Later on, you'll come to find work is the product of force and distance. Force in newtons, distance in meters. Or the conventional units for work or energy, which are joules. As we close, we can confirm whether our formula, first formula, was correct by substituting or confirming our working with our second formula. We see whether it will be able to give us the same answer or a different answer, such that we can now have in our bank the two formulas that we have been presented with, that work or energy of a spring is the product of force times extension divided by 2, or the product of the spring constant times extension squared divided by 2. So as we close, learners, again, work is equal to a half KE squared. And therefore, our K, we found it to be 20 newtons per meter. And then the extension we have found is 2 meters. Remember, we are squaring this extension squared. So if we were to cancel the units for meter, and then dividing by 2, we are going to have 1 times 20 times 2, which will take us to 40. And that confirms to us that the two formulas for finding work or energy of springs as a half force times extension or a half K times E. In these, learners, we have covered extensively the Hooke's law, starting from the statement in which he found out in his experimental activities, Robert Hooke found out that force is proportional to extension. Force is directly proportional to extension. And in this, we said it only happens within a certain limit, provided you do not exceed the elastic limit. We have again gone ahead in working constant given force and extension, or working force given the spring constant and the extension. Again, we have carried that knowledge with us in working the total extensions we obtain whenever we arrange springs either in series or arranging them in parallel, in which springs assist each other. And finally, we have concluded the content on Hooke's law in establishing the formulas that we use in working out work or energy possessed by springs that are carrying some weight on them and exhibiting a given extension. Until next time, my dear learners, we conclude at that point, hoping to meet you very soon. Further questions can still be forwarded to KUTV live program. Those questions are going to reach the teacher. The communication will be channeled back in a similar manner, and it is going to reach learners. We are not confining ourselves to only the topic on Hooke's law. I'm a teacher of physics. And therefore I can comfortably guide in all areas, having an experience of 11 years since I graduated from Kenyatta University, and therefore feel free to consult whenever whenever need arises. Continue keeping safe and observing all the protocols that we have been advised by the Ministry of Health. See you, learners.